Learning objectives. In this chapter, the user will learn the following in detail: color models, pseudo-color, image processing, color transformation, segmentation. Basics of full color image processing. Two major categories. Processing of each component image individually leads to composite processed color images. Work with color pixels, vectors directly. The matrix for vector in RGB color space is shown on the screen. Per color component and vector-based processing equivalent if the process is applicable to both vectors and scalars. The operation on each component of a vector is independent of the other components. This figure shows the spatial masks for grayscale and RGB color image. Color fundamentals. Color image processing. Extracting features of interest in an image, an area that has been gaining in importance because of significant increase in use of digital image over Internet. Motivation to use color. Powerful descriptor that often simplifies object identification and extraction from a scene. Humans can discern thousands of color shades and intensities compared to about only 24 shades of gray. Two major areas. Full color processing. For example, images acquired by color TV camera or color scanner. Pseudo-color processing. Assigning a color to a particular monochrome intensity or range of intensities. Some of the grayscale methods are directly applicable to color images, others require reformulation. Color fundamentals. The picture shows the color spectrum as seen by passing through white light through a prism. The next figure shows the wavelengths comprising the visible range of the electromagnetic spectrum. Perception of colors by the human eye. Cones can be divided into three principal sensing categories. 1. Roughly red. 2. Green. 3. Blue. About 65% are sensitive to red light, 33% to green light, and about 2% to blue. Colors are seen as a variable combination of the primary colors red, green, blue. From CIE 1931, wavelengths blue 435.8 nm, green 546.1 nm, and red 700 nm. Figure shows the absorption of light by red, green, blue cones in the human eye as a function of wavelength. Primary colors can be added to produce the secondary colors of light. Magenta, cyan, yellow. Mixing the three primaries in the right intensities produce white light. Primary colors of pigment. Absorbs the primary color of light and reflects or transmits the other two of magenta, cyan, and yellow. This figure shows the primary and secondary colors of lights and segments. Characteristics of color. Brightness embodies the achromatic notion of intensity. Hue, attribute associated with the dominant wavelength in a mixture of light waves. Saturation refers to the relative purity of the amount of white light mixed with a hue. For example, pink is less saturated, the degree of saturation being inversely proportional to the amount of white light added. Chromaticity. Hue and saturation together. Color may be characterized by its brightness and chromaticity. Tristimulus values. Amounts of red, X, green Y, and blue Z needed to form a particular color. A color can be specified by its trichromatic coefficients. Small x equals caps x by x plus y plus z, y equals y by x plus y plus z, z equals z by x plus y plus z. Note, x plus y plus z equals 1. Another approach for specifying colors. The CIE chromaticity diagram shows color composition as a function of x, red, and y, green. For any value of x and y, Z, blue, is obtained by Z equals 1 minus x plus y. Pure colors of the spectrum, fully saturated, boundary. The figure shows the chromaticity diagram. Typical range of colors, color gamut produced by RGB monitors. The figure shows the typical color gamut of monitors, triangle, and color printing devices, irregular region. Color models. Color models are also called as color spaces or color systems. Purpose of color models: facilitates the specification of colors in some standard way. Color model: specification of a coordinate system and a subspace within it where each color is represented by a single point. Most commonly used hardware-oriented models. RGB, red, green, blue, for color monitors and video cameras. CMY, cyan, magenta, yellow, and CMYK, CMY plus black, for color printing. HSI, hue, saturation, intensity. The RGB color model. Each color appears in its primary spectral components of red, green, and blue. Model based on a Cartesian coordinate system. Color subspace equals cube. RGB primary values at 3 opposite corners, plus secondary values at 3 others. Black at the origin, white at the opposite corner. The figure shows a schematic of the RCB color cube. Number of bits used to represent each pixel in the RGB space equals pixel depth. Example: RGB image in which each of the red, green, and blue images is a 8-bit image. Each RGB color pixel, that is, triplet of values RGB, is said to have a depth of 24 bits, full color image. Total number of colors in a 24-bit RGB image is 28 cube, that is, 16,777,276. The figure shows the RGB 24-bit color cube. Figure shows generation of RGB image of the cross-sectional color plane. This figure shows the 3 hidden surface planes in the color cube. Acquiring an image is a reversed process. Using 3 filters sensitive to red, green, and blue, respectively. For example, try CCD sensor. Color image acquisition, color mono CCD, and Bayer filter mosaic. Demosaicing. Interpolating the values of missing pixels in the component images. The matrices of demosaicing are shown on the screen. The other models: nearest neighbor method, demosaicing by median filter, demosaicing by constant hue, demosaicing by gradients detection, adaptive interpolation by Laplacian. XYZ CIE. Official definition of the CIE XYZ standard, a normalized matrix, is as shown on the screen. Commonly used form W by O leading fraction RGB equals 1, 1, 1 leads to Y equals 1. The CMY and CMYK color models. CMY, cyan, magenta, yellow, secondary colors of light or primary colors of pigments. CMY data input needed by most devices that deposit colored pigments on paper, such as color printers and copiers. Or RGB to CMY conversion, the matrix is as shown on the screen, assuming normalized color values. Equal amounts of cyan, magenta, and yellow leads to black, but muddy looking in practice. To produce true black, predominant color in printing, a fourth color black is added. CMYK model, CMY plus black. The RGB and CMY color models are as depicted on the screen. The HSI color model. RGB and CMY models. Straightforward plus ideally suited for hardware implementations plus RGB system matches nicely the human eye perceptive abilities. But RGB and CMY not well suited for describing colors in terms practical for human interpretation. Human view of color object described by hue, saturation, and brightness or intensity. Hue describes a pure color, pure yellow, orange, or red. Saturation gives a measure of the degree to which a pure color is diluted by white light. Brightness, subject to descriptor, practically impossible to measure, embodies the achromatic notion of intensity. Intensity, gray level, measurable. HSI color model, hue, saturation, intensity color model. Intensity is along the line joining white and black in the RGB cube. To determine the intensity component of any color point, pass a plane perpendicular to the intensity axis and containing the color point. Intersection of the plane with the axis is the normalized intensity value. Saturation, purity of a color increases as a function of distance from the intensity axis. On the axis, saturation equals 0, gray points. The figure shows the conceptual relationship between RGB and HSI color models. This figure shows the hue and saturation in the HSI color model. From the diagram, the dot is an arbitrary point. The angle from the red axis gives the hue and length vector of the saturation. The intensity of all colors in any of these planes is given by position of the plane on the vertical intensity axis. The HSI color models are based on triangular color planes and circular color planes as shown on the screen. Conversion from RGB to HSI. The equations are as shown on the screen. Conversion from HSI to RGB equations are also shown. The images on the screen show the conversion from HSI to RGB. Manipulation of HSI images. In the figure, RGB image components correspond to its HSI image: hue, saturation, intensity. Modified HSI image. The L star, A star, B star model. Example of color management system, CMS. CIE L star, A star, B star model, or CIE lab. The equations for this are as shown on the screen. The L star, A star, B star color space is colorimetric, colors perceived as matching or encoded identically. Perceptually uniform, color differences among various hues are perceived uniformly. Device independent. Other characteristics: not a directly displayable format. Its gamut encompasses the entire visible spectrum. Can represent accurately the colors of any display, print, or input device. Like HSI, excellent decouple of intensity, represented by lightness, L star, and color, A star, for red minus green, B star for green minus blue. Here we can see how Microsoft adds colors using RGB and HSI color models. Colors can be described in many different ways, each method based on a color model. For example, the RGB color model is based on creating colors by adding together various amounts of red, green, and blue light. The Microsoft Expression design lets you specify colors by using any one of the 5 different color models: RGB, HSL, HSB, CMYK, and HEX. You can select a color model with the Choose Color Picker drop-down list at the bottom of the color picker. RGB color model. RGB is an additive color model, which means that the more red, green, and blue you add, the closer the color becomes to white. When you mix an equal amount of red, green, and blue, you always get a neutral gray. To make a color darker, remove equal amounts of all 3 colors. Computer scanners and monitors are based on the RGB color model, so it is a natural model for describing color on a computer, especially when you work with scanned images. The value for each channel, red, green, or blue, can range from 0, no color, to 255, fully saturated color. RGB color is also sometimes named 24-bit color or millions of colors. HSI. Many people find the HSI color model more intuitive because it defines colors based on hue, saturation, and intensity. To specify a color, you can pick its hue on a rainbow spectrum, select its saturation, the purity of the color, and set its brightness, light to dark. Bright red is highly saturated bright color. Pastels such as soft pink are less saturated. You specify hue by a degree, 0 to 360 degrees, and specify saturation and lightness with percentages from 0 to 100%. Any HSI color with 0 saturation is a neutral gray. Color transformations. Context of a single color model. No conversion between models. Formulation. G of x, y equals T of f of x, y, where G of x, y is a processed color output image. T represents the operator defined over a spatial neighborhood of point x, y, and f of x, y represents the color input image. The basic transformation of the color mapping function is as shown on the screen. Example: modify the intensity of the full color image using the equation as shown on the screen. This is shown for HSI, RGB, and CMY. Color complements. Hues directly opposite one another on the color circle is called a complement. Complements are analogous to grayscale negatives, useful for enhancing detail embedded in dark regions. The complements on the color circle is shown on the screen. Color slicing. Highlighting a specific range of colors to separate objects from surroundings. Display the color of interest or use the region defined by colors as a mask. If colors of interest are enclosed by a cube or hypercube of width W and centered at a prototypical average color with components A1, A2 to AN, then the equation will be as shown on the screen. Highlight the colors around the prototype by forcing all other colors to the midpoint of the reference color spaces. For example, middle gray in RGB, 0.5, 0.5, 0.5. The images show the color slicing transformations that detects reds within an RGB cube of width W equals 0.2549, reds within an RGB cube of radius 0.1765, centered at the same point pixels replaced by cube and sphere. Tone and color corrections. Effectiveness of these transformations judged ultimately in print, but developed, refined and evaluated on monitors. Need to maintain a high degree of color consistency between monitors used and the eventual output devices. Device-independent color model relating the color gamuts of the monitors and output devices. Tonal transformations. Typical transformations for correcting three common tonal imbalances are shown on the screen. Color balancing. Goal: move the white point of a given image closer to pure white, R equals G equals B. Example of strongly colored illuminate, incandescent indoor lighting, yellow or orange hue. Using white may not always be a good idea. Analyze a known color in an image with white areas. Accurate visual assessments are possible. Other example, skin tones. Color balancing corrections for CMYK color images are shown on the screen. Histogram processing example. Histogram equalization in the HSI color space is represented on the screen. Pseudo-color image processing. Assigning colors to gray values based on specified criterion. The term pseudo or false color is used to differentiate the process of assigning colors to monochromatic images from the process associated with true color images. In the figure, A to C represent modified HSI component images and D shows the resulting RGB image. Intensity slicing. It is the simplest example of pseudo-color image processing. If an image is interpreted as a 3D function, the method can be viewed as one of placing places parallel to the coordinate plane of the image. Each plane then slices the function of area of intersection. The figure shows the geometric interpretation of the intensity slicing technique. An alternative representation of the intensity slicing technique is also shown. Gray level to color transformations. Basically, the idea underlying this approach is to perform three independent transformations on the gray level of any input pixels. This method produces a composite image whose color content is modulated by the nature of the transformation functions. Piecewise linear functions are used to generate the colors. Smoothing and sharpening. Color image smoothing SXY, set of coordinates of a neighborhood centered at x, y in an RGB image. Average of the RGB component vectors in this neighborhood. The related matrix is as shown on the screen. This can be carried out on a per color plane basis, same as averaging using RGB vectors. Color image sharpening. In RGB, the Laplacian of vector C is as shown on the screen. This can be computed on each component image separately. The figures show image segmentation based on color. Segmentation in HSI color space. The images will be as shown on the screen. Segmentation in RGB color space. Given a set of sample color points of interest, obtain an average color to segment RGB vector. Segmentation. Classify each RGB pixel as having a color in the specified range. Generalization of the distance measures, where C is the covariance matrix of the samples representative of the color we wish to segment. The three approaches for enclosing data regions for RGB vector segmentation is as shown on the screen. Example: compute mean vector of color points in a rectangle. Compute the standard deviation of red, green, and blue values. When the box points to red, the dimensions along each RGB axis. Conclusion. In this chapter, we have covered the following in detail: color models, pseudo-color, image processing, color transformation, segmentation.